Okay. Oh, testing. Can anyone hear me? Hi, everyone. Thanks so much for letting me speak here and for coming to this talk. I guess I'm wearing a mask probably because I was sick a few days ago, feeling much better, but just in case, I have a mask on. So for those of you who don't know me, I work on sort of algorithms for sampling from high-dimensional probability distributions. And I mainly work in a discrete setting, partly motivated by sort of statistical physics and statistical inference applications, but also because, in my opinion, sort of the discrete setting, it's much less understood. Because, for instance, in continuous world, things like convexity all make sense, at least in sort of a natural way. Okay. So today I want to tell you about a joint work with Zongchen Chen, Nitya Mani, and Ankur Moitra on sort of a problem that is very near and dear to my heart. And that's the problem of sampling or counting graph colorings. Okay. There's the problem. So I have a graph G. Also, please interrupt me at any time if you have questions or anything. And also, if you can't see it or if I'm not clear on anything. So I have a graph G. And let's say it's a sparse graph. So I have a bound on its maximum degree. And I have some integer q. And my goal is to sample a uniformly random q coloring. Okay, so just to make sure we're all on the same page, just recall a q coloring is an assignment of colors 1 through q to the vertices, such that neighboring vertices do not get the same color. Okay, so this is a very fundamental example of a constraint satisfaction problem. Okay, good. Okay, so sort of a long-standing conjecture in the field of approximate counting and sampling says that this task is solvable as long as the number of colors I give to you exceeds the maximum degree. Okay, so this is a conjecture to the Jerem from like 30 years ago. It says that if q is at least the max degree plus 1, then and max degree plus 1 is, it's a very natural threshold, right? This is the threshold at which a simple greedy procedure will find you a color. Okay. Now, let me say a few words on like why I think this problem is very interesting. So I'll start first. You might be wondering, like, well, why do we care about such a problem? I mean, I guess first thing first is just that this problem is very intimately tied to the structural properties of the uniform distribution of colorings. And these structural properties, which I will get to later in this talk, they also have applications beyond the problem of counting and sampling. Okay. I guess for me, one thing I really that's sort of really attracting to this problem is that it exhibits what physicists call a phase transition. So here I have a parameter q that I can vary and roughly sort of scales the difficulty of the problem. And it turns out that at least conjecturally, problem exhibits what we call a phase transition. So let me first, so phase transition. So right at around, so this is a x-axis denotes the values of q. And I have this natural threshold, delta plus 1. And it's known that in this regime, it's actually NP hard to sample, even if the graph I give you is triangle free. So the significance of this assumption, triangle freeness, is just that if the graph is triangle free, I can still find a coloring with much fewer colors, roughly delta over log delta, many colors. But even though I can find such a coloring, I cannot sample uniform, I cannot count such things. Okay? So really, delta plus 1 is sort of the threshold for the onset of hardness. Okay? And it's known that at least above some number of colors, roughly twice the max degree, okay, you can do a little better than this, that we have sort of fast algorithms, like nearly linear time algorithms. And conjecturally, we also have linear time algorithms here. So conjecturally. Order of n log n. Okay, so at around delta plus 1, the complexity jumps from nearly linear to exponential under a standard complexity theoretic hypothesis. Okay. And I guess this also sort of explains why this problem is actually quite difficult, because any method you use to analyze whatever algorithm you want, it's going to start blowing up at some point. And the question is trying to make sure that it blows up really just at the critical transition point. Okay. But I guess sort of this problem fits into a much broader theme. Or a broader theme, which I find fascinating. So, I have so this is some distribution over stuff, over colorings or whatever. And you can apply various, heuristic methods inspired by, say, physics or whatever, to make predictions about the structural properties of your distribution. And sort of a theme here, or of this line of research is, or I guess really the fundamental question here, do these kind of heuristic predictions actually have very concrete complexity theoretic consequences? A more fundamental question, a broader fundamental question. When do sort of heuristic physics-based I guess, yeah, and a third reason I find this problem interesting is that it also raises a question of randomness versus whether or not randomness is necessary. So, of course, the sampling problem inherently requires randomness. I mean, it's baked into the problem itself. But you can ask the question of whether or not randomness is needed for the equivalent problem of counting the number of colorings. Okay, so it turns out counting the number of colorings is equivalent to sampling a uniformly random one. Okay? And you can ask whether or not randomness is needed there. And at least conjecturally, no. And we conjecture it's not needed. And this has been vindicated in sort of simpler models that are not quite colorings. Okay. Good. Okay. So what is known? Let me just say a few words about what the existing works have shown. So it turns out already, when Mark Jerram made this conjecture, he was already able to prove that if you've studied Markov chains, sort of the first technique, path coupling, you use that technique to show that if number of colors exceeds twice the maximum degree, and get efficient sampling. Over the years, there's been many works trying to bring the number of colors down, either by adding extra assumptions to the graph or just trying to improve on this constant in general. Okay, so of note, I'll mention a couple important milestones in this line of work. So from Eric Gode from 2001, and more recently, yes, just to save some time and space, a team of 5 people, Chen, Delcourt, Moitra, Paranal, and Posel from 2019, managed to bring this down to 11/6 minus some epsilon times the maximum. And this epsilon is roughly 5. If I tell you if I give you some, if I tell you the graph is triangle free, we can do a little better. So, roughly 1.7. Okay, so this is roughly speaking the current state of the art, although it's not possible for me to list all of the work steps. Study this. Okay. So what is the algorithm that we're going to be studying in this work? So we're going to study the classical Markov chain Glauber dynamics. This is a Markov chain on colorings, and it proceeds by the following simple procedure. In every step, I select a uniformly random coloring, uniformly random vertex. And I'm going to resample the color assigned to that vertex condition that everyone is. So in other words, so currently I'm at some coloring, I pick a random vertex, right? And currently my neighbors, they're assigned some colors. So those are the colors I'm not allowed to use. But of all the other colors, remaining ones, I pick one of them uniformly at random. Of the ones available to me, I pick one uniformly at random. And we'll be mainly interested in studying the mixing time of this Markov chain. So here's the main result. So what we basically show is we get down to basically the conjecture threshold if we assume the graph has sufficiently large girth. So we prove the following. So for every epsilon larger than 0, say Glauber samples uniformly random Q coloring in nearly linear time. We say as long as we're just ever so slightly above maximum degree, maybe a 1 plus epsilon times maximum degree. And as long as the girth of the graph G something mild, so roughly 1 over epsilon squared log of the maximum. Just recall the girth is the length of the shortest side. Okay. So notably, the girth requirement we have here is independent the size of the graph or the number of vertices of the graph, right? So if we're thinking everything here is being constant, epsilon, some possibly small constant, and the maximum degree is also just some constant, 5 or 6 or something. Okay. So we have sort of a girth lower bound that's a constant independent of everything. Okay. So any questions about the problem or the statement of this? Okay. I guess perhaps more importantly, what we do is we establish sort of a key structural property. Oh, yeah. Go ahead.
Can you, is there some intuition as to why small cycles are bad for Glauber dynamics?
Yeah, good question. So I guess it'll become more clear as I tell you, for instance, the proof outline. Roughly speaking, we'll try to reduce the problem to a problem on trees. where things are much easier because local neighborhoods are easier for trees. Yeah, basically, but I guess it will become more clear. And also, for instance, a lot of these predictions are based off of looking at the behavior of random colorings on trees. More questions? Yeah. Good question. So right now, yeah, so it's believed that growth assumptions are not needed. Okay? So this is the last, yeah, so this is still an open problem. We're still working on this. More questions? And so we're on the way to establishing this, we've sort of proved a sort of a key structural property of the distribution over random colorings, which is sort of essential for a lot of, for instance, of a lot of algorithms for these types of problems. Okay, so even for a lot of deterministic algorithms that people have developed over the years, relies on this kind of property. This property is something known as correlation decay. Okay, so roughly speaking, it says something like the following. So it says that if I have two vertices in the graph, I have, let's say, let's say it this way. Let's see, for all pairs of colors, that sort of knowing one, whether or not one vertex is assigned a given color has a negligible amount of influence on the assignment of the other vertex. So in particular, if I tell you that, say, the vertex U is assigned the color B, and I ask for what is the probability that the vertex V is colored C, and I compare this with the same probability where now I don't tell you what U is assigned. This sort of correlation between U and V is small, and in fact, exponentially small in the distance between them. So of course, neighboring vertices, they'll have strong influence on each other, right? But what we want to formalize is that vertices that are far away from each other actually have very small influence on each other. So this is some kind of influence or like correlation. And we're saying correlations decay in distance. Okay. Good. And it's kind of a surprising thing that actually, prior to our work, this type of structural property wasn't even known for trees, at least in its strongest form. Yeah, go ahead. Yes. Over a random color. So this is a property of just that specific history. I guess theorem set on trees. Strong version. So we have a strong version of this correlation decay. Always as long as, okay, delta plus 3, it's not quite the conjectural threshold, but it's like basic. Yeah.
Under the assumptions of the setting given the theorem, like you would have,
yeah.
If it's a path, then
Mm-hmm.
it's probably random coloring.
Yeah. So of course, this type of property is only going to be able to hold if the number of colors is like larger than, say, yeah. So when number of colors is below the maximum degree, it's known as this property fits. And that's actually one of the reasons why hardness, sort of get hardness. So I guess I should say a few words about this. So this is actually a little bit surprising because so the previous best here was, trees are, so simple in some sense, right? And they're entirely described by a certain function, which I may or may not describe to you during this talk, but a certain sort of low dimensional function sort of fully describes the behavior on trees. And sort of, I don't know, like, I guess in my mind, just trees are so simple. So like, how could this have been open previously? But I guess just say a few words on what people have proved previously. So Jonassen, back in 2002, he proved the weak version. I guess, allow me not to get into too much details of what strong versus weak mean here exactly. But he proved the weak version for just the infinite delta regular tree. Down to the conjecture threshold. But his proof was actually rather complicated and actually also required significant, it was like computer assisted and everything. And then more recently, for 2019, the strong version. When Q is larger than 1.5. But besides this, there's not so many results. Stretch. Okay. And then I guess the second ingredient of our result then goes by sort of lifting this analysis on trees to general purpose. Okay. So now I want to spend sort of the next 10 minutes sort of giving you a rough outline of the argument. And I guess, yeah, just to give you a sense of how these types of results. So. So basically, sort of the main theme behind sort of the line of reasoning is sort of local to global in some sense. Okay, so we're going to sort of gradually reduce the problem down to more and more sort of local statements. For instance, local in the sense of being around like questions about like around the neighborhood of a vertex. Okay, so our end goal, of course, is sort of rapid mixing. Glauber dynamics. This is a rather global statement in the sense of like sort of the expansion of the space of all colorings. Okay. So by our previous work, we can reduce this to a problem about a certain limited correlations property about the distribution, something called spectral limits, which for the purpose of this talk will be defined as follows. Okay. So for every vertex U in the graph, and for every pair of colors B and C, okay, if I look at sort of the total influence of this vertex U on all the other vertices, that this is a bounded quantity. Okay. I sum over all the other vertices in the graph, and I look at the total variation distance between the conditional marginal distribution, given that U is assigned color B, compared to the same thing, except now I assigned color C to vertex U, semi-squared. So just like remark about notation, so mu throughout is going to be uniform over colorings. And then subscript meaning I'm looking at sort of the marginal distribution induced on the colors assigned to a single vertex. Say it this way. And then superscripting just means condition. Okay, so I sample a random coloring condition on knowing that vertex U is assigned V, and I look at sort of what the distribution over color is assigned to V. Okay? And I'm just comparing the total variation distance between these two conditional marginal distributions. Okay? So is the meaning of this okay? Clear? Okay, good. So this is still like a relatively global statement in the sense that I have to look at every single vertex and I look at the influence of the vertex on all the other vertices in the graph. I want to reduce this further. So let me first say, okay, so let me first say it sort of informally. So I mean, ideally, what I would like is to just directly reduce this to correlation decay. In the sense that, let's say, total variation distance between these two things is, let's say, exponentially smaller distance. Ideally. And such a thing, if we had this property for general graphs, then at the very least, intuitively, it should imply something like this, right? So imagine that, say, your graph G was something like the lattice, for instance. Okay. If I had this property, then I can bound this quantity by just summing over all vertices at various distance scales from the vertex U, right? So in particular, summation is total influence will be upper bounded by something like the summation over all distance scales, the number of vertices at that distance scale times something that's exponentially small in that distance. Right? And if I'm on a graph like a lattice, where the number of vertices only grows polynomially fast, then this exponential decay is going to completely wash out the growth in the number of vertices. Right? And that's good for us. That's roughly some intuition of why you expect correlation decay to be helpful here. Now, of course, this argument definitely does not work if, let's say, I'm on an expander, where the number of vertices is growing exponentially fast. And that could completely defeat the decay of correlations, right? It could grow faster than the rate at which correlations decay. Roughly speaking, you already see like one theme of, or one challenge we must overcome here. Roughly speaking, we need sort of the decay of correlations to win out compared to the growth of, so the number of like susceptible vertices, you know, if you imagine some kind of like infection process, you know, on the graph. Okay. So we won't reduce it to exactly this. So what we want to do instead, we'll reduce it to a condition that essentially formalizes the fact that the decay of correlations wins out. Okay. So the more precise statement is the so there exists, say, some radius which is less than the girth f over 2. It's just to ensure that the ball of radius r around this vertex is a tree. such that, for all vertices U, for all colors, pairs of colors, B and C, if I just look at the vertices at distance R from U, at the same influence quantity is sufficiently small. So it's roughly, let's say, okay, if you like, 1/100. So then again, think of R here, the girth is some constant, right? Some constant depending on the maximum degree and epsilon. R is smaller than that. So I'm looking at just the constant radius ball around the vertex. And I just want to say that the influences have decayed enough relative to the size of this ball. Okay. So already I've sort of reduced, I haven't told you how, but I've reduced a statement about an entire graph to a problem about just roughly radius R neighborhoods. Okay. And this will be implied by, now I'm looking at, a ball of radius R around a vertex, U, right? And locally it looks like a tree because I've assumed that the girth, I've assumed something about the girth, right? Now we reduce this further to correlation decay on trees. Now let me be a little more precise about what I mean by correlation, what I want to correlate this statement. Okay. So for all trees rooted at, say, a vertex U, the following two statements. Okay, so first is just that the analogous statement for this thing is so that if I sum over all, let's say for all R, if I sum over all vertices at distance R, the influence of the root on the vertices at distance R is small. And it's in fact decaying. And then I guess the rate of decay will also be a little bit more precise here. Okay. And I want one more thing. That the influence of all these vertices on the root is also small, also decay. Okay, so for every, let's say, a pair of partial assignments on the boundary of this ball, the probability that the root is assigned, say, some color C, condition on tau, and compare it with the same thing, except condition on tau prime, and this is also exponential. Okay, so two kinds of correlation decay. So yeah, so I guess the picture looks like this. I have a tree of height R, rooted at U. I want so a bound on the total influence of the roots on everybody at distance R, and a bound on the total influence of everyone at distance R on the root. And then finally, we can then reduce this further to a statement, the following statement. Okay, so here I'll be a little bit informal here. So for one hop. So and this is contraction of something called belief propagation. You know what this is. also known as the tree recursion. Okay, so this part of it, and then this is of course then going to be implied by the assumption that the number of colors is sufficiently large. Okay? So I don't want to get into too many details of this proof. I want to tell you more about some of these other arrows here. But let me just say like a few quick words about what exactly this means here. Okay, so on a tree, one of the reasons that trees are extremely nice is that they admit sort of a very natural dynamic programming algorithm for counting. Okay, in particular, there's a way to sort of, if I want to know, say, the marginal distribution of a vertex U, then I can compute it if I know the marginal distributions of its neighbors. And so this gives me a recursive algorithm. Okay? So in particular, there is a certain sort of multivariate function that consumes as input a set of D probability distributions and spits out another probability distribution. Okay? And what we want from this map is that it is sort of a contraction. And so this is now like a purely analytic statement. I have some function, I just want it to be a contraction. Yes. Good question. Yeah, very good. So what I mean here is that actually, so if I look at just the subtree rooted at a vertex, right? If I know the marginal distribution of this vertex with respect to just that subtree, then I can compute the marginal distribution of U for this entire tree. And the nice thing about tree is that I have independence, because once I've deleted this vertex U, these subtrees are now disconnected from each other. And so there's no, the joint distribution is like a product measure. There's no correlations. Okay. So I don't want to get into the details of saying what exactly this multivariate function is, but roughly speaking, there's some very explicit multivariate function which we have to prove is a contraction. And that in itself actually is also extremely non-trivial, but I don't want to get into too many details there. But let me also say one more thing, which is that this is actually how a lot of the physicists make predictions, which is actually they study how this function behaves. Okay? And in fact, they even restrict to the setting where all of these distributions here are all the same, which sort of corresponds to the infinite deregular tree. So I guess since I haven't defined anything, I'll put it in quotes. Yeah. Okay, so this is the rough structure of the argument. And so the plan for the rest of the talk is for me to tell you about some of these other arrows, which are, I guess, mainly these two in here. I guess I should mention that one of my collaborators, Nitya Mani, she actually gave a talk on this result at IIS maybe a few months ago, but the bulk of her talk was focused on this part of the proof. And so if you really are interested in that, go see that one. So I'll talk about the other arrows. Okay. If I won't talk about this, then I can probably erase this. Let me just sort of restate my goal now. So my goal say the following, right? So for all vertices U in the graph, for all pairs of colors, the total influence of this vertex U on everybody else is okay. And I guess it turns out it suffices to prove something following stronger statement that for every vertex and for every pair of colors, we're going to exhibit a coupling of these two distributions, the two conditional measures. Let's see. Let's call this gamma, such that an expectation, if I sample a pair of colorings from this coupling, that the Hamming distance, the number of disagreements between these two random colorings is small. And I guess the implication from this statement to this one is sort of just a direct application of the coupling. So it's a cute little exercise. So I guess this is where I'll do something extremely risky, which is try to project something. Okay, good. Okay, so what have I drawn here? So what I just said was I want to design a coupling of two conditional distributions, basically of two random colorings, such that it minimizes sort of the expected Hamming distance. Okay, so the picture you should have in your head is the following. So I have, this is my two graphs, and in one of the graphs I've colored vertex R, I guess that should be U. I've colored the vertex U with red and the other one colored with blue. And what I want to do is I want to sample two colorings, a coloring of each of these things, in a coupled way, such that the number of vertices that receive different colors is small. And the rough scheme of how we're going to design this coupling is going to do it iteratively, starting from a vertex and going sort of outwards in distance. So what a coupling might look like is the following. So maybe what I try to do is I'll try to couple, I'll first sample the colorings for the local neighborhood. Okay, maybe some of the, I'll generate some colorings that maybe disagree, some of them might agree. And then from there, maybe I'll sample the next set of colorings. Okay? So the orange blob here is just all the vertices that have disagreeing colors. And I'm going to keep going as I sort of move outwards in distance, in graph distance. Okay? And what I hope is that after a while, the number of disagreements die out. And in particular, my hope is that they will all be contained within a constant radius ball around a vertex. Because once I can confine all the disagreements to a constant radius ball, then everybody outside of this ball will never feel any of the disagreements, right? Because, right, they can't access the interior, right, just by conditional independence, right? And so if I really can confine all the disagreements to this ball, then that gives me a certificate saying that the number of disagreements is small. Because everybody else can be coupled perfect. Okay, so this is a rough scheme for how this coupling is going to work. Okay, now of course, we need to prove that it actually does, die out. That the number of disagreements really does that. Okay. Oh, I thought oh. Thanks. Okay, good. Okay, so I guess okay, for this, I can erase this. Here's one. Let's make a first attempt at this. Assume like that version of correlation decay holds on trees. Then for all graphs of girth G, for all radii less than half girth, are the following statement. So if I look at the total variation distance between the marginal distribution induced on the radius R sphere, and I compare it with, two different conditionings, but this is small, that this is like, exponentially smaller. Sorry, I should stop. Okay. This is the first attempt at sort of going from analysis on trees to analysis on graphs of sufficient large girth, right? So what's the idea? I mean, basically our assumption, I'll just say a proof sketch, but it's not. So our assumption is that our assumption is that, for all pairs configurations on this boundary, maybe let's say implies that for all pairs of, partial colorings on the boundary of this ball, we have sort of, the total variation distance between marginal distribution of condition on knowing the values of the boundary on U, L prime, this is small. Right? This is just because, if I look at my ball of radius R, locally it looks like a tree, right? And so if I tell you what the colorings are assigned to the boundary of this ball, then it's like as if I just look at it as a tree, right? That has this topology, and I assigned colorings there. Right? I never see any of the non-tree part of it once I tell you what the coloring is of everyone on this boundary. All right. So once you know this, then you can sort of do your classic, Bayes rule tricks, right? To convert, to swap the conditionings and sort of the events. Right? Then do Bayes. It requires just a little bit of calculation. Okay. Now this is but I don't want to get into too many details here because it's not the most interesting part. Okay. But let's just use this very directly, that sort of local neighborhood or local radius R ball is just a tree. Okay, so if I have this lemma, then here's like a very natural attempt at a couple. Okay. Okay, so what this tells me is that there is a coupling of the colorings of a radius R ball, such that with very small probability that they disagree somewhere. Okay. So first step, I sample two partial colorings from TB optimal coupling of these two conditional marginal measures. And then once I have an assignment of colors to all the vertices in this boundary, then I sample everybody else. Let's say I guess it won't matter so much how we couple this because, this thing won't work. And that really comes down to the first step, but maybe let's just go case by case here. Okay? So the good case is that, of course, we got the same coupling, or the same coloring, right? So tau equals tau prime. And this happens with probability at least 1 minus, that thing. Okay. So in this case, then I have achieved what I wanted, in the sense that I've confined all the disagreements to everything inside the ball, right? Everything outside of the ball, all they will ever see is the partial coloring assigned to the boundary, and they agree. So I can couple them perfectly, and we're done, right? So probably all disagreements will be inside this radius R ball. And because R, big R is a constant, then my number of disagreements will be at most, let's say, delta dr, which is, again, constant. And we're good, right? Now, of course, the bad thing is there, again, capital R is a constant. So even though you think of this as a small number, it's still a constant probability that this thing fails, right? So with constant probability, I could get something that are different. And a priori, this bound tells me nothing about how many disagreements there are between tau and tau prime. Right? It just tells me that they're not equal, right? So in particular, there could be this many disagreements between tau and tau prime, in which case the number of disagreements could then propagate uncontrollably to everyone else in the graph. Right? Is that okay? Questions? So in that case, tau not equal to tau prime, no control on the Hamming distance between tau and tau. Okay. So what we really want is not just that with small probability that they disagree, but also that sort of the expected behavior is that only a constant number of disagreements appear on this boundary. Okay. We want something, a bit more refined. There's no lemma. And this will be sort of, maybe associates. So make the same assumptions as before. Then for all radii, we improve something better than this. So if I sum over all vertices in the radius R ball, influence of U1 to V. This is upper bounded by something that goes like 1 minus epsilon R plus 1 minus epsilon to the G over 2 times delta to the R. Okay. So let me just sort of help you parse this. Okay. So imagine my graph G literally was a tree. Okay. So it's not just that it has large girth, but it actually was a tree. Then my assumption already tells me that I get this bound even without this term here. Right? This one here. Right? This thing will literally say what I want here, even without this term. Now, of course, my graph here is not actually a tree, right? It only has large girth. So think of this some kind of error, right? So what roughly the proof strategy for this lemma goes as follows, right? So if I could truncate, like literally just like chop off, all the vertices outside, distance, say girth over 2, then I'll get this thing. I can't actually do this truncation, but I can kind of approximately implement this truncation by randomly coloring the vertices at distance g over 2. And with just this amount of probability, this random coloring, so this approximate implementation of this truncation is going to sort of fail. So I guess in the interest of time, I will not prove this lemma. But I can sort of roughly say that once you have this kind of lemma, what the coupling then looks like. Again, just think of this as sort of, this is small, as long as girth is like larger than r times log delta. So then the girth will just be another constant. The capital R is a constant. So now here's basically a coupling. And what we'll do is we'll sample a random vertex. In this radius R ball. And then we'll sort of do the TB optimal coupling to color this vertex. So. And then I guess recurse. And now, basically, we'll have a very good bound on the probability that that this vertex, really gets the same color in both instances. And you can work through all sort of the quantifiers and everything, but I guess I'm running a little bit over time, so I guess I'll probably stop here, and I'll take questions, and we can, of course, discuss details offline. Thanks for your attention. Sorry, say again, small what degree? Sure, but our girth lower bound is actually very mild, right? It's sorry, I guess I'm not sure. I'm totally sure I understand the question, but I don't think you can use sort of at least that amount of large girth to say anything more about the sparsity than what we've already assumed. Maybe you can take it offline. Sorry.
Physical intuition for the correlation decay.
Physical intuition. Yeah, I see. I guess the physicists love their belief propagation, and so they analyze sort of the analytic properties of that thing, and they even analyze sort of like a very restricted form of that recursion. I guess, right, and you can use that to then make predictions about when this correlation decay happens versus when it doesn't. Yeah.
This example in which correlation decay fails in small girth case.
The small. Harder to analyze. I mean, we believe the correlation decay holds even without this girth assumption. So really, it's really an issue of the number of colors that determines when.
I guess you talk about the propagation part.
Yeah.
How sensitive is it to like being a tree? Like if you have like a tree with like one extra edge or something, could you still somehow like make this thing work by just saying, oh, this extra edge is not going to change that much. Maybe your girth isn't good, but like there's only like one small symbol.
Yeah, so I think our analysis is pretty robust to this kind of thing. I mean, once you move past this one edge, then yeah. But I guess there weren't like sort of natural and like nice graph classes that have just like one.
Like, how many of these implications are like even approximately in like the reverse direction? Like, do you know if Glauber dynamics implies some sort of spectral independence, some sort of correlation?
Yeah, good. So there are some implications known. So if you know Glauber mixes in n log n steps, and you know your graph has sub-exponential growth, so like the lattice, then there's actually an equivalence between correlation decay and fast mixing of Glauber. But as for like, most graphs, expanders, whatever, there's no such thing. I mean, it's typically you open up the proof of correlation decay and use that to deduce correlation decay, and then also fast mixing. But that's a very nice question to see, which is like, whether or not, say, spectral impedance or these things are, yeah, basically whether these are equivalent to each other. That's a nice question. Thank you.